Okay. Okay, so let's continue. Remember we said that this diminishing marginal rate of substitution is kind of linked to the right convexity of the indifference curve, right? But we said not only convexity, but we said strict convexity, right? So basically we don't want flat portions if we want diminishing marginal rate of substitution. Okay, so let me give you the definitions of convexity, concavity, and such, so it will be like a nice recall of those concepts. But here's the thing. So remember I said that it's like if we have diminishing marginal rate of substitution, it is equivalent to saying that indifference curves are strictly convex, right? But this is something that we say about the level curve, right? We say about the indifference curve. So what can I say about the utility function? What do you think? So this, right, we said something about the indifference curve, right? It's convex. But what should be the case for the utility function so that we would have diminishing marginal rate of substitution? Do we know? No, we don't know, but just guess. What could be the case?
Isn't it also convex?
So do you think?
I think it might be both convex and
so actually, you see that in order to have diminishing marginal rate of substitution, you need to have at least, okay, the utility function can be concave, it's enough, but concavity, it could be a little bit more general than sort of concavity, what we call quasi. Okay, quasi-concave. So we actually require a strictly quasi-concave utility function. Okay, so I'll tell you what it means. So that's going to be hard to explain to your grandma, but again, we'll try. Okay, but basically, so let's write these things down. Okay, first, just like this is kind of a note where we should remind ourselves, the concepts of convexity, concavity, and such, okay? But we can link the diminishing marginal rate of substitution concept to convexity, okay? And let's do that, okay? So the first thing that we would be doing is that I'm going to give you the definition of a convex set, okay? So you'll see why. So this is the definition, okay? And this is the definition of a convex set, okay? So basically S, right? So this is, so it's a set in Rn, let's say, is a convex set, okay? Basically what you do, if for all x1 element of S and x2 element of S. So you take 2 points, okay, so in this set. And then what you do is you take what we call a convex combination of them, okay? So basically t x1 plus 1 minus t x2, okay? For all t, so let's say such that t is between 0 and 1, okay? So convex set, it means that you take 2 elements of this set and you take a convex combination of them, and this convex combination also should lie in S. That's the definition of a convex set, okay? So what does that mean? So let's try to see, for instance, so examples. Suppose my S is this. Okay, so suppose this is my set. I actually take 2 points in this set. That's what it says. Connect them. If this line segment stays within the set, we call that set convex, right? So you see that this is the case, right? I take 2 points, I connect them. This, like this line segment stays within the set, right? So this is a convex set. So, but what about a set like this? Is it convex? No. Why? So you see that this should be true for any two elements of this set. So here I can take one element here, right? I can take one guy here. I connect them. You know, like some portion of the set, some portion of the segment is actually outside the set, right? So this is actually not convex, okay?
The connection should be linear. Can we connect with a curve?
No, but you are taking a convex combination, right? So it's exactly. A convex combination is also a linear combination, right? So this is basically the case, right? So this is actually the case, right? So this is a convex set. This set is not a convex set. So first, we're going to link diminishing marginal rate of substitution concept to the convex sets, okay? So let me write this down. So let's move on here. So let me write this down. So basically, diminishing marginal rate of substitution is equivalent to saying this. So I'll write this and then we'll see. Now, so let's write this. So diminishing marginal rate of substitution, okay, is equivalent to, okay, so assuming, let's say, all bundles, okay, of xy, of x and y, that are indifferent to, let's say, a particular x star, y star, right, form a convex set. So I wrote this, but what does this mean? We actually know a nicer way of saying this, right? So apparently diminishing marginal rate of substitution is kind of equivalent to assuming that all bundles, right, that are indifferent to any x star, y star, they form a convex set. How do we call the set of all bundles that are indifferent to a particular, all bundles, so that are preferred or indifferent to, okay? We have to have that, so otherwise we won't have the set that we would like to have. So all bundles that are preferred to or indifferent to a particular x star, y star form a convex set. How do we call the set of all, like bundles which are either preferred or indifferent to x star, y star? How did we call that set? Now, how did we call that set? Remember, how can we say, what is this? When we say that, all the bundles which are either preferred or indifferent to. We call that better than is preferred. But if in order to include indifferent to, we said, what was it called? At least as good as, right? So now this is actually, it means that at least as good as set is convex, okay? So basically this is actually this. So this guy here, right, all bundles, right? All bundles that are preferred or indifferent to a particular x star, y star. This basically means that, right, at least as good as set of x star, y star, right? So basically, apparently, this set should be a convex set, okay? So this is the first link that we're going to make. So you can actually say this at least as good as, okay, sets convex, okay? Again, it's also strictly convex, but we'll see, okay? At least as good as sets are convex, okay? So let's actually write this, for instance. So let's actually have this. Maybe I'll have it here. So this is basically, so let's have this here. So this is, let me give you some examples. So this would be much better. So I put here y, I put here x, okay, and I have my indifference curve. Let's say this is a utility level u1, okay? And suppose I have my x star here and I have my y star here, right? So what is the set of all the bundles which are either preferred to x star, y star, or indifferent to x star, y star? Where is that set? Right above the indifference curve, right? So it's here, right? So this portion we call, right? So this set here we call at least as good as set, okay? So this portion we call it at least as good as set, okay? So that's how we call it. So basically, what does it mean, at least as good as set? So it's defined as set of all bundles, right? So basically, that's what we said, all bundles, right, that are preferred or indifferent to x star, y star, okay? Is the set convex? Is the set convex? So remember how were we checking this? We were taking 2 points. I take 2 points and I connect them. If this line segment stays completely within the set, we say it's convex, right? So this is convex, right? So it's convex. So we basically here, this is a case where it is convex, right? Do we see diminishing marginal rate of substitution here? Yes, right? So you see we have this nice, nice shaped indifference curve, and we see diminishing marginal rate of substitution, right? You see that it is a case where this at least as good as set is convex, okay? Now check this one out. So suppose I have this x, y. I have an indifference curve like this, okay? And let's call this, like u1, u2, whatever, u1, okay? And then suppose I have an indifference curve like this. And by the way, in the previous class, because I drove it in such a way that, oh, hocam, if we have, like something like this, it's violating more is better, some of you. But do you think this is violating more is better? Do you think this violates more is better? We should think, right? So it's if it were like this, you're right? Then you can actually say that, oh, hocam, for instance, this and here, this guy more of x and more of y, right? So it's violating more is better assumption. But if I draw this in such a way like this, such that there is no point where, like you can get more of, so for instance, if you check this and this one out, right? It's again have this slope, right? So it's not positively sloped anywhere, right? It's always like this. So do you think this violates more is better? Right now, no, okay? So apparently we can have an indifference curve like this, okay? And it could still satisfy more is better. But what is the at least as good as set here? You said, oh, hocam, it's the set of all bundles, right, that are here. So this is the at least as good as set. Is this set convex? No, right? Remember, what did we say? Pick any 2 bundles, okay? I pick one here and another one here, connect them. You see this, some portion of this segment lies outside the set, right? So this is not convex, right? Actually, this is should be strictly, you know why we mean strictly, right? To guarantee the diminishing. So you said, do we see diminishing marginal rate of substitution here? Not everywhere, right? So here we do, but here, not really. So for instance, here, things are changing, right? The slopes are, in some portions, the slopes are, the absolute value of the slopes are increasing, right? Instead of decreasing, they're increasing. So you see that here, it's not, at least as good as set, is not convex, right? So we don't see, not, we don't see diminishing marginal rate of substitution, okay? So let's say we don't see diminishing marginal rate of substitution everywhere, right? So here we don't see diminishing marginal rate of substitution, but here we see diminishing marginal rate of substitution, okay? So you see that you can link the concept of diminishing marginal rate of substitution to the, like to the sets at least as good as sets, to the convexity of the at least as good as sets, right? So that is one way of saying it, okay? Yes?
You assume that at least as good as sets are convex, that contradicts with these.
Yes, so if there is no diminishing marginal rate of substitution
So
here.
it's not the absolute assumption. Right?
So it is, you see that we said the diminishing marginal rate of substitution is equivalent to this, okay? So you see that when you don't have this guy, you might not, it doesn't necessarily require that you have diminishing marginal rate of substitution, okay? So, and here is the case, right? So this is actually, so these are equivalent sayings, okay? So that is one way. Now, but remember, this is convexity of a set, right? So first we define the convexity of a set, but maybe you will say that, oh, hocam, we have, like we want to also see the convexity of the curve, right? So the function. So we say indifference curve should be strictly convex, right? So let's define those so that you would have it in your notes, the definition of convexity. And then you'll see I'll provide you all the links between them. But the first link that we figured out, this diminishing marginal rate of substitution, it actually means that at least as good as sets are convex, actually strictly convex, okay? So basically this is the case. So now this is going to be, so let me actually give you the definition of a concave function. So these are all side notes, okay? So this is actually concave function. So a concave function, so we call f a concave function when it satisfies this property, okay? So f, so basically, okay, maybe you remember. So let's put here y, x, and is this function concave? Okay, so let's keep this in your mind and let's write the definition and then let's try to see whether it's concave, okay? So suppose you have a function, so x is actually, so which is, suppose f is a concave function, okay? If for all, okay, so just keep this in your mind, I'll draw this again, okay? For all x1 and x2 element of x, okay? We have this, f of t x1, 1 minus t x2. I take a convex combination of these guys, and then I look at the value at this numbers, okay? If it's concave, it actually says that it should be greater than the convex combination of the values, okay? For all t element of 0, 1, okay? So this is concave function. So what does this mean? So remember my function. So according to this definition, do you think it's concave or no? So let's try to see. Let's try to apply the definition. It says that if it's concave, what should be the case? It says that, so remember this is the one that I draw. So this is y, x, so this is sort of f of x, right? You can put here f of x if you want. And I have a function like this. So what does this tell me? It says that, so take any x, right? So let's suppose this is x1 and take any x2. Take their convex combination, okay, I take, right? And it says that if that for that convex combination of them, for all t, right? For all these numbers, the value of the function, right? So it's actually, and you take any convex combination of these guys, and you look at the value of this. It says that the value of these guys' convex combination should be more than the convex combination of f of x1 and f of x2, right? So this is, and this should be true for all t, right? So this should be true for all the convex combinations, right, that you take. So does this satisfy that condition? Yes? No? Maybe? Does it? Yes, right? So it satisfies. So it is concave, right? You see that when I take their convex combination, so some point in between here, I look at the value of that point. The value of that point would always lie above this line segment, right? Which is the convex combination of the values, okay? So basically, so this is this case. So this is the concavity definition. So if you want to make this strictly concave, so first let me put it, then you have to adjust this definition a little bit, okay? So here is how you are going to actually adjust it. If you want to make this strictly concave, that's why I write it in green, okay? So if you want to make this definition strictly concave, then is a strictly concave function, okay? So then you say that for all, so you make these adjustments, okay? For all x1, which is not equal to x2, you have, so let's actually, which is element of x, okay? So then this convex combination, how do you think I should modify it? Whenever things are strict, it means that you need to get rid of the equalities, okay? So basically it says that this is going to be a strictly concave function. If you take the same point, then they would be equal by definition, right? That's why you have to modify the definition saying that, or take not any 2 points, but take just 2 points which are not equal to each other, okay? And then for those 2 points, what should be the case? This should be strictly greater than, right? This guy. And then I should adjust it somewhere else too. Because if I take t equals to 0, what's going to happen? So when I'm taking convex, if I take t is equal to 0, this is f of x2, right? Then this is 0, this is 1, f of x2. Can I say that f of x2 is greater than f of x2? I cannot. Then what should I do? How should I modify the condition? I should get rid of, exactly, this guy, I should make it like this, okay? I should get rid of all the equalities, okay? All these stuff. So this is how you would make it strict, okay? Now let me give you the definition of convex. Again, it's going to be very similar. So let's say convex function. Now guess, what is a convex function? Now I have to modify this definition. Like what? Right, so I have to make for convex, I have to make it less than or equal to. In order to have strictly convex, what should I do? Get rid of the equality, right? So basically that is the case. So let's write this. F R is a convex function, okay? If for all x1 and x2 element of x, okay, we have f of t x1 1 minus t x2 should be less than this time t of f of x1 1 minus t f of x2, okay, for all t element of 0, 1, okay, closed interval. And again, in order to make this strictly convex, then again you said that, oh hocam, here I have to get rid of for all x1 which is not equal to x2 element of x, okay? So let's put it like this, okay? Element of x, this should be less than, right? And then I should make this t element of 0, 1, okay? So this is how you would make convex. So then this function was concave. then which function is going to be convex? If I draw it, so let's put f of x here, it's going to be, right, something like this. Is this convex? Let me try, right? What does it say? Pick any, suppose this is x1, this is x2, pick any 2 points, right? Take their convex combination, which is here, and check the value of that function. The value of that function should be below the convex combination of the values, right? So basically this is convex, right? So actually, and do you think in this case this is strictly convex, concave, and this is strictly convex? Do you think we have the strictness here as well? Yes, right, because it's strictly above, right? There are no flat portions. So if I had drawn this like this, suppose it had some flat portions, then it would be just, like for instance, let's say I have something like this, and in some portion it's flat, and then it goes like this, right? If it has some sort of a flat portion, then in that portion it might not be strictly convex, okay? So just keep this in your mind that this is the definition of a convex function and a concave function, okay? And you saw the difference for the strictness, okay? Now, okay, so this is what we said. So now let's actually learn another thing. So remember we said that, but this is something about what we were saying is that diminishing marginal rate of substitution. So here's another link. So we said that diminishing marginal rate of substitution, it actually means that indifference curves are strictly convex. Okay? Now, but remember, this is saying something about indifference curves, the level curve. What if we needed to say something about the function, right? Utility function. Then what does it mean about the utility function? So this guy, if you would like to know it for the utility function should be what? Concave, convex, like it turns out that it should be at least what we call strictly quasi-concave, okay? So now I'll give you the definition of quasi-concavity, okay? But apparently it turns out that it should be utility function, so at least, okay, a quasi-concave, strictly quasi-concave utility function, okay? Apparently. If you have apparently a strictly quasi-concave utility function, the indifference curves that you get are convex, okay? So before I give you the formal definition, let me tell you, what does quasi-concavity mean, okay? So suppose you have, remember I told you that suppose I get a cup and I put it in this classroom, okay? Like this. So it's like a dome, right? You know what dome is, right? What does it mean? Kubbe, right? So it's like a dome. Suppose I put a dome, I brought, Hagia Sophia's dome here in this classroom, right? And like this, I put it here, okay? So that is, suppose that's your utility function, okay? So you see that you have the, good x here, good y here, and then you have the right, so the utility level, right, as your third dimension. So suppose I put the dome here. So if I slice these, if I at some utility level, right, so let's say, so this is u of xy, at some utility level, right, I just slice this function, okay? And remember, I sliced it, I put it here on this xy plane, right? So it would look like, so if I do it, on the xy plane, or let's put it like this if you want, so this is going to be x, so let's put it right, and then let's say this is y, and suppose you have the dome, like here, so this is y, this is x, right? Suppose I took a slice of it and then I projected it on the xy plane. The slice would look like this, right? But then, fine, but so now I flip it, so I draw it here, okay? So let me have y here, I have x here. So I'm talking about stuff like this. But do we have indifference curves like this? Did we draw? How did I draw them? I got rid of the top portion, right? So why do you think this is the case? If I have an indifference curve like this, what's going to happen?
More is not better.
Right, so it's not, so you would immediately tell me that, oh, hocam, it could be the case, right? I could have a utility function which is like a dome here, and I could get a slice of it and then projected it on the xy plane. But then it would be a case where more is better is violated, right? So suppose this is an indifference curve. So that's why if there is more is better, we get rid of this portion, okay? But you see that this has nothing to do with more is better, right? We never said that it should be the case, okay? But basically that's what we do. So that's why we get rid of this top portion and draw the indifference curve like this, okay? So you see that, so if you get, but apparently, so if you have a dome, okay? So this dome is actually a concave function, okay? So when you have a utility function like this, this is concave. But it turns out that in order to have these nice indifference curves like this, you know, this nice slice, you don't have to get basically a concave one, okay? But you can actually get, you know, you can have cases like this. What is this? This is like a cone, right? So you can actually get a cone, even, you know, like you can actually get something weirder than this. You can actually get a pinched cone, right? Instead of having a cone like this, you can have something like this, right? A little bit, a cone where you have, right? So like the sides are kind of curved, okay? Pinched cone. So this is the, so it means that in order to have these kind of, you know, like indifference curves, it's enough, you don't have to actually have this dome. It's enough to have this guy, okay? So that's why we say, so this guy is actually a quasi-concave function, okay? This pinch cone. So this is how you would, you know, like visualize it. So because you wouldn't like the definition, okay? So this is much better. So you see that it means that you can have a pinch cone, right? If you have a pinch cone, if you sliced it, again, you would have nice indifference curves, right? Nice convex indifference curves, okay? So just keep this in your mind. It corresponds to a case basically of like a pinched cone. We can allow for a pinched cone, okay? Something like this. So this is concave, but this is too strong. We don't have to have a dome all the time. We can have something like this, okay? So this is what so it is linked to the quasi-concavity, okay? So let me put this down. We have our nice stuff. So let me write down the definition of quasi-concavity. And then, so this is a little bit, you know, like too many definitions, but don't worry, it's going to be over, okay, soon. But you see that all of them, they all have a meaning, right? Economic meaning. So this is what we would like to do. So basically, let's try to say that quasi-concave, okay, so let's say utility function. Apparently, this is what we need. Okay, a quasi-concave utility function. So let's say actually define the quasi-concave function. Let's do it like this. Let's be general, okay, quasi-concave function. So I'm going to give you these definition, okay? So I'm going to give you two definitions and you could see the links, okay? So the first one is F is quasi-concave. Okay? If and only if we said superior sets, so I'll tell you what superior sets are convex sets. Okay? What is a superior set? So let me write this for you. So suppose you have a function, you know, like f is from x to r, okay? And suppose you have, so this is a set. So let me define. It's consisting of all the x's such that the value of these x's are actually greater than or equal to y star, okay? So superior set is actually this. So you pick a level, right? You pick a level, let's say 5, and you try to look at all the points whose values are more than 5, right? This looks like what? Suppose this f is a utility function. I pick a utility level, right, which is 5, and then I look at all the points which give either 5, utility, either 5 or more. The superior sets they look like what? Superior sets are actually, this is similar to what we have said before. Something that we have said. What is it?
Convex.
No. Let me actually tell you this. So superior sets is basically, it says that suppose f is utility function, okay? Its superior set is a set, sort of, you see here. So let me actually be proper. So exactly. So that's what I was looking at, right? So this is a superior set for level y star, okay? So this should be the case that superior sets are convex sets for all y star element of R, okay? Exactly, so the superior set, because what does it say? It says, suppose f is u, pick a level, right? It says that pick a y naught, which is, let's say, 5, pick a number, basically. For any number that you pick, you look at all the bundles which give more utility than 5, right? And you look at the set of all these bundles which give more utility than 5. It says that the set of all the bundles which gives either more utility than 5 or the same utility, right, as 5. Basically, it says that these sets are, this is like an at least as good as set, are convex, okay? So apparently, so this definition is similar to what we have said before, but this is, you see the link between the quasi-concavity and the fact that you have at least as good as sets being convex, right? And also, or if you want, I can give you another definition which is similar to those guys, okay? And this is basically, so let me put it like this. So this is a superior set, okay, for level y star. Okay, so this is a superior set for level y star, and that should be true for any, like any level sets. All the basic, it says that all the superior sets are convex. Or we actually say that f is quasi-concave, okay? And then said that if and only if, again, for all x1, x2 in x, okay, we have this f of tx1 plus 1 minus tx2. What do you think should be the condition? Now it's not concave, right? It's quasi-concave. So what should be the condition? It's hard, so it's okay. I didn't know it either, okay? When I first learned about it. It's actually similar to that, but not really. It's actually related to the minimum, okay, of those guys. So basically, minimum of f of x1, f of x2, okay? So basically, this is the case for all t element of 0, 1, okay? So if I want to do this strictly quasi-concave, what should I do? Now you know the trick. If I want to make this strictly quasi-concave, what should I do? I should do this for all x1, which is not equal to x2 in x, right? And then we say this is greater than, and then here we say t is element of what? 0, 1, but open, right? So that's it. These are not tricky questions, okay? So this is, so don't worry. Don't be afraid to say stuff, okay? So this is basically how you do this strictly quasi-concave. If you want to make this quasi-convex, then what should we do? Now you know the trick exactly. Now you're going to change the, right? So if you want to make this quasi-convex, then this is going to be less than or equal to. And if you want to make this strictly quasi-convex, then you know you need to get rid of the equalities, okay? So basically this is the case. So this, I would leave it to you. F is quasi-convex, okay? If and only if. So you have all these stuff, but what you do is you say less than, and if you want to make this strict, you know the trick. Strictly quasi-convex, right? So you make this less than here, and then you get rid of all those equalities, okay? So this is basically how we define. Okay, so now too many, definitions, but now you know what they mean, right? So that's why so concave function apparently means that we have a utility function like a dome here, right? Quasi-concave means that we have a utility function not exactly like a dome, but maybe like a pinched cone, okay? So we can allow for that. And all of these just to have those nice, strictly convex indifference curves, okay? Because those indifference curves, you're going to see that will be, they say some stuff to us, and they will be helpful in dealing with, like, you'll see, okay? They're going to give us a lot of information. Now, what I should do is that I'm going to combine all these guys together, and then I'll write it down, and then I will try to explain again to your grandma, okay? You will try to explain to your grandma what these strict convexity means, okay? It has a nice meaning. So now, let's do this. And let me actually write this down. So, okay, I'll write these again so that you would have it nicely written in your notes. So this, okay, so we said that there is this concept called diminishing marginal rate of substitution, okay? So how can we link this diminishing marginal rate of substitution? Then we said that this is apparently equivalent to, what was the first thing that we said? This is sort of equivalent to, in terms of at least as good as sets. What did we say? We said at least as good as sets are, remember if I had the diminishing marginal rate of substitution, we said that at least as good as sets are convex, right? So basically this is what we said. So let's write this, at least as good as sets are convex. So this is one way of achieving, apparently, diminishing marginal rate of substitution, or saying there is diminishing marginal rate of substitution. So these are equivalent to each other, okay? And then we said another thing. What did we say? You can either express it in terms of sets, or we said that if there is diminishing marginal rate of substitution, indifference curves are what? Convex, right? Strictly convex. That's what we said. So it is actually equivalent to strict convexity of indifference curve. Okay? Fine. But this is something about the indifference curve. If we want to go a little bit further and say something about the utility function, what did we say? In order to have diminishing marginal rate of substitution, we should have a utility function, which is at least quasi-concave, right? Could be concave. So don't forget this. So suppose a function is concave, okay? Suppose f is concave. Do you think f is quasi-concave as well? Yes, right? Don't forget that if something is, concave, it's also like a concave function, right? So it's so put it like this: f is concave, then it's also quasi-concave. But do you think the other way around is correct? So if it's something like a concave function, it means it's not exactly concave, right? So this side doesn't work, okay? So always keep in mind. So which means that concavity is actually a stronger assumption, okay? So here we don't need that strong assumption apparently to have, convex indifference curves or to have diminishing marginal utility. but you need to have apparently at least a strictly quasi-concave, or you don't have to write this, but what I'm saying, at least you need this, right? If you have a concave one, it's already quasi-concave, so it would be satisfied. So at least a strictly quasi-concave utility function, okay? So apparently this is the condition that you need to impose on the utility function, and which would correspond to a condition of strict convexity on the indifference curve, which would correspond to a condition, if you want to talk about the at least as good as sets, it would mean that these sets are again strictly convex, okay? And which would mean diminishing marginal rate of substitution, okay? So this is the link between all these guys, all these mathematical concepts. Apparently they all lead us to this diminishing marginal rate of substitution case, okay? Now, so let me actually tell you this, and then we'll give a break because this is important, okay? So what do you mean by, if I have convex indifference curves, right, strictly convex indifference curves, how can I tell this to my grandma? So again, back to the, like interpretation of this. How can I tell this to my grandma? Suppose I have an indifference curve like this, right? So which is strictly convex. I put here y, I put here x, and I draw an indifference curve like this at this u bar utility level, whatever, okay? So what does this mean? If I want to explain this to my grandma, she doesn't know, oh, grandma, your utility function is strictly quasi-concave, and then, I mean, even you would be like, what is that? You cannot tell her that. So what does this mean? You know one explanation, but there's actually another explanation, which is, I think, really nice. So one explanation, you said that, oh, grandma, the more x you have, right? Actually, you would be willing to give up less and less y to get one more x, right? That is one explanation for the strict convexity of the indifference curves. But what else can you actually tell to your grandma? If her, like indifference curve is like this, what does this mean? For instance, let's have this. And in terms of the convexity, right? So we said that if it's convex, I combine these guys, and then any convex combination lies above this curve, right? Basically, it means that. What does it mean? Suppose I have a bundle here, x1, y1. Suppose I have a bundle here, x2, y2. Suppose, again, this is like drinks and pizzas. So here you have, let's say, just one beer and like 20 pizzas. And here you have, let's say, 20 beers, and you have here only 2 pizzas, okay? So what does this mean? It means that, for instance, if you have 5 pizzas and 5 drinks, right, which is, let's say, a convex combination of them, okay? Or if you want, let's put it like this. Suppose you have x1 plus x2 over 2 here, which is a convex one, y1 plus y2 over 2 here, right? It says that the value of this convex combination, right? So what is this? So what does it say? So it says that like if you have some sort of a mix in between, okay? Then what does it say? It says that it gives more utility or less utility. So it is, so let's have it like this. Suppose this is 5, this is 15, okay? So this would be better. And this is also, let's say, 15, and this is 5, okay? Suppose in one case you have 5 drinks and 15 pizzas, let's say for the whole class, okay? And then here you have 15 drinks and 5 pizzas. What does it say? The entire class would prefer, what is for instance, the midpoint of these guys? 10. 10 pizzas and 10 pizzas and 10 drinks. What does this say? Does it give more utility or less utility? So if it goes up, so this is 10, apparently. So think, okay? So we're going to discuss it in the next class, right?
Quasi-concave function çizseniz yani bu iki boyutlu mu yoksa üç boyutlu mu? QuasiConcave.